All right, so get this. We're going to be diving deep into states space models. Those AI models that were like supposed to be amazing at handling tons of information, those long sequences. Well, turns out they might have a little bit of a memory problem.
Yeah, that's right. And this research paper we're looking at today, it's called Understanding and Mitigating Bottlenecks of State Space Models. And it really gets into some surprising limitations, particularly recency bias and oversmoothing.
Okay, so recency bias. That sounds interesting. This paper talks about something called an influential score, and it's supposed to measure like how much each input element affects the model's output. So even though SSMs are, designed for these long sequences, they seem to have a strong preference for recent information. Huh.
It's wild, right? What's really fascinating here is that Theorem 3.1 in the paper actually proves that this bias is like built into how SSMs work. It's not just about, the training data, it's like baked into the math. Essentially what happens is that older data gets forgotten like crazy fast, exponentially fast.
So it's almost like the model's memory is like a fading echo, right? Where the most recent sounds, they're crystal clear, but those older ones are almost like inaudible. Okay, but wait. What about those selective mechanisms used in Ramba? Wouldn't those counteract this? Those are designed to like zero in on the most relevant info, right?
You'd think so, but the research shows that even like advanced SSMs like Mamba still exhibit this recency bias. This suggests that the bias is way more fundamental to the architecture itself. It's like you're trying to build a house on a foundation that's totally tilted. No matter how much you decorate, that tilt is always going to be there.
Gotcha, gotcha. So, okay, let's say I'm using an AI chatbot that's powered by an SSM. Does this mean it might just like forget the beginning of our conversation?
It's totally possible. If the model is like heavily biased towards recent inputs, it might have trouble retrieving information from earlier in the conversation. To test this, the researchers did this really clever experiment. They called it needle in a haystack.
Needle in a haystack. Okay, you got to tell me more about this.
So imagine you have this really long document, a haystack of information. And hidden somewhere in that document is a specific statement, like the needle. The researchers wanted to see if SSMs could find that needle no matter where it was in the haystack.
So they were testing the model's ability to like use context from the entire document, not just the most recent parts.
Exactly. And to make things even trickier, the statements they used, they actually had like deliberate factual errors in them, like the capital of France is Madrid, to make sure the model wasn't just relying on memorized facts. They wanted to force it to use the information from the document.
That's pretty clever. So what happened? Were the SSMs able to find the needle?
Well, Mamba-based LLMs, which are those large language models built on SSM architecture, they really struggled to retrieve statements that were like placed earlier in the document. It was almost as if their vision was limited to that most recent portion of the text. Now, transformer-based models, they consistently found the needle no matter where it was. No sign of this positional bias at all.
So transformers passed this test with flying colors, while SSMs kind of stumbled a bit. Does this mean transformers are just like better at handling those long-range dependencies?
Well, it's not that straightforward. See, both architectures have their own strengths and weaknesses. So while transformers did really well in this task, they can be super computationally expensive to train and run. SSMs, on the other hand, they have potential advantages in efficiency and scalability, but we've got to address these limitations, this research revealed.
Yeah, this recency bias, it seems like a pretty big deal. It's not just about forgetting things. It's also about those SSMs potentially being vulnerable to manipulation, right? Which is a little concerning.
You're spot on. This is where things get even more interesting. Think about like image classification, where a model is analyzing an image to, figure out what's in it. So the researchers did these experiments on a data set called CFAR10, where they subtly like changed some pixels in the images.
So like changing a few brushstrokes in a painting, you might not even notice the difference, but it can totally change how the AI sees the image.
Exactly. And what they found was that messing with those pixels at the end of the sequence had a way bigger impact on Mamba's accuracy than changing those at the beginning. Actually, like corrupting just the last 32 out of 10 linear 24 pixels caused Mamba's accuracy to like tank. It dropped by over 80%.
Whoa, that's crazy sensitive. Like the model's like totally fixated on that most recent input and just ignores the bigger picture. What does this kind of sensitivity mean for language models?
Well, it raises some serious red flags. See, language models rely on instructions. They're called system prompts, and they guide the model's behavior. And typically, these prompts are placed at the beginning of the input.
But with this recency bias,
Yeah.
couldn't someone manipulate the output just by adding like some sneaky instructions at the end, essentially overriding the initial prompts?
That's exactly right. It's like whispering a secret message at the very last second to like sway someone's decision. And that's a huge concern, especially as AI systems become more integrated into our lives, right? We need to make sure they're robust and can't be manipulated so easily.
Definitely. Okay, so we have this recency bias that makes SSMs kind of forgetful and potentially easy to manipulate. So what if we try to make the model stronger, like add more layers, make it deeper to boost its memory? Wouldn't that help?
Unfortunately, it's not that simple.
Okay.
This actually leads us to the second big limitation discussed in the paper, the problem of over-smoothing.
Over-smoothing. Okay, I'm not familiar with that. What does that even mean when we're talking about AI?
Okay, so picture this. You've got a palette of different colored paints, each with its own, unique vibrancy. But as you mix those colors together, what happens?
Well, they blend together. They all turn into one, like, dull color. You lose all the variation.
Exactly. And that's what happens in SSMs when you add too many layers. All those internal representations, it's like the way the model sees the data, they become way too similar. It loses its ability to distinguish between different inputs.
It's like all those memories are blending into one big blur. No wonder it can't remember specific details. But I thought adding layers was supposed to, like, help the model see further back in time, extend its receptive field.
You're right. Depth is usually good for capturing those long-range dependencies, but too much depth leads to this over-smoothing. And Theorem 4.2 in the paper, it describes this mathematically. It's a tricky balance. We need depth, but too much of it can be bad.
So we've got these two big limitations.
Yeah.
Recency bias
Yeah.
and over-smoothing. Are researchers just, like, giving up on SSMs? There's got to be some way to fix these, right?
Researchers are definitely not giving up. In fact, the paper talks about a potential solution that could address both of these problems, and it's called polarization.
Polarization. Wait, isn't that something to do with magnets?
It is, but in this case, it means something totally different.
All right, I'm all ears. Explain this polarization thing.
So the basic idea is to have two special channels in the model's memory. It's like having two separate notebooks. One for carefully recording every single detail you've learned, like a history book, and another one for jotting down immediate observations, like what you're experiencing right now.
So one for the past, one for the present. How does that help?
By keeping these two channels separate, the model can access both that long-term history and that immediate context without them, like merging into one big mush. And this helps with both recency bias and oversmoothing.
That's pretty clever. It's like having a super highway for past memories and a separate express lane for that current info. But does this polarization actually work, like in real life?
The researchers tested it using, those associative recall experiments we talked about earlier, where the model has to retrieve info from long sequences of key value pairs. And get this, with polarization, Mamba was able to access information from way further back in the sequence. It was a huge improvement.
Wow, so there's hope for SSMs after all.
Absolutely. This research is still pretty new, but polarization seems like a promising way to unlock the full potential of SSMs for tackling complex tasks that need both long-term memory and, like, a sharp focus on what's happening right now.
This is getting pretty complex. So just to recap, we started talking about how SSMs are supposed to be great at remembering, but this research uncovered some serious limitations.
Yeah, we talked about recency bias, where the model's like obsessed with the newest info and forgets the past, and then over smoothing, where adding more layers actually makes it harder for the model to tell the difference between inputs.
Right, and both of those can make the model less reliable and maybe easier to trick, which is a little scary considering how important AI is becoming.
For sure. But hey, researchers are already working on solutions, and this polarization thing seems pretty promising. It's an exciting area of research, and I'm really curious to see how it develops.
Well, this has been a really fascinating deep dive into SSMs. We've explored their potential, their limitations, and a possible path forward. But there's still so much more to unpack, right?
Totally. In part 2, we're going to get into the nitty-gritty details of polarization and like how it works. We'll also talk about what these findings mean for the future of AI.
Stay tuned.
Welcome back. We're continuing our deep dive into the wild world of state space models and their interesting memory quirks.
Right. Last time we were talking about polarization and how it might help SSMs get over that recency bias and that whole over-smoothing thing. So how does it actually work, like technically? Okay, I'm ready to get a little nerdy here.
Okay, let's break it down. Remember those two special channels we talked about, one for holding on to past information and one for focusing on the current stuff. Well, to make that separation happen, researchers are suggesting we tweak some specific elements within the model's state transition matrices.
Whoa, whoa, whoa. Slow down a sec.
Yeah.
Matrices. Can you explain that in a way that even like a non-math person can understand?
Sure, think of these matrices like a really complicated network of pipes, and each pipe carries information from one part of the model to another. So by setting some of these pipes to always open or always closed, which means like forcing some elements to be 1 or 0, we can control how the information flows through the whole model.
Okay, I think I'm getting it.
Yeah.
So by strategically opening and closing these like information pipes, we create dedicated pathways for different types of memory.
You got it. The always open pipes make a direct route for preserving those long-term memories so they don't get overwritten by the new stuff coming in. And those always closed pipes, they help keep the current input separate so it doesn't mess with the long-term memory storage.
It's like having a special highway for those long-term memories and a separate express lane for the newest info. Pretty clever. You mentioned earlier that polarization was tested with those associative recall experiments. What are those exactly, and how did polarization do?
Remember how Mamba had trouble pulling information from those long sequences of key value pairs? Well, associative recall tasks are designed to test exactly that. And with polarization, Mamba's performance in these tasks was like way better. It could accurately grab information from much further back in the sequence. It's like suddenly opening up a hidden archive in the model's memory.
Wow, that's awesome. So does this mean polarization like completely solves those memory problems we were talking about? Are SSMs ready to take over the AI world?
Hold on, let's not get ahead of ourselves. While polarization is definitely promising, the research is still pretty new. There are still tons of questions to answer, like how do we know the ideal number of those polarized channels? Is 2 the magic number, or could more be even better?
Right, it makes you wonder if like too many polarized channels could actually make things worse. And how does polarization work with other parts of the architecture?
That's another area that needs more research. Like, remember that H3 architecture we talked about? Could that help or hurt polarization? These are all things researchers are looking into right now. It's a super fast-moving field.
This is all so interesting. But let's switch gears for a bit and talk about like the real world stuff. How could all this impact the AI we use every day?
Imagine a world with smarter chatbots, ones that actually remember your entire conversation, not just the last few things you said. Those interactions would be so much smoother.
No more repeating yourself a million times. Sign me up. What else?
What about financial models that can analyze decades of market data, not just the latest trends? We could have way more accurate predictions and less risky investments.
That would be huge for the financial world. What about in healthcare?
Think about AI systems that can consider a patient's entire medical history, not just their most recent tests. That could lead to super personalized treatments and better outcomes. The possibilities are pretty mind-blowing.
Those are some really cool applications. But with all these potential benefits, what about risks? We talked about manipulation before. Does polarization help with that?
It could potentially make AI systems more resistant to some types of manipulation. By shielding that long-term memory, those system prompts might be less vulnerable to those bad instructions.
It's good to hear. But even if we figure out the manipulation problem, are there other things we need to be thinking about, ethically speaking, especially with AI that could remember everything?
You're right. We definitely need to think about privacy, especially with AI that has these amped up memory abilities. If a system can access and remember tons of personal information, we need some serious safeguards in place to protect people's privacy and make sure that data isn't misused.
It's like that classic sci-fi problem. With powerful technology comes great responsibility. We need to be developing these tools ethically and carefully.
Exactly. We always have to think about the ethical side of things as we explore and develop things like polarization. It's not just about making AI more powerful, but about making AI that helps humanity and doesn't go against our values.
So for those of us who aren't AI researchers but who use AI all the time, what does all of this mean? What's the takeaway?
It means we're entering a new age of AI, one where these systems are becoming more capable, more complex, and maybe even more impactful on our lives. It's a world full of amazing possibilities, but we've got to stay informed about both the good and the bad.
So it's about staying curious, staying involved, and staying informed. Sounds like there's still a lot more to talk about.
Oh, yeah, definitely. In the final part, we'll wrap up this whole polarization discussion and explore some big questions about the future of SSMs and that whole debate about which architectures are best for dealing with those long sequences of information.
Can't wait. Stay tuned for part 3 of our deep dive into state space models.
And we're back, wrapping up our deep dive into state space models. It's been a wild ride exploring their potential, uncovering those memory quirks, and of course, diving into that polarization thing.
Yeah, it has been pretty fascinating, hasn't it? Polarization does seem like a real game changer, a potential fix for those issues of, recency bias and oversmoothing. But as with any powerful tech, there are always those what-if questions, like, what do these findings mean for the future of AI in general?
Right. That's a great question. I feel like we've only just, scratched the surface here. If we know that some AI architectures have these like built-in biases, should we be rethinking how we design these systems from the ground up?
It's definitely worth thinking about. Maybe we need to come up with completely new architectures or, explore those hybrid approaches that combine the best of different models while, like, minimizing their weaknesses.
So like building an AI dream team where each player brings their own unique skills to the table. I like that analogy. Exactly. This research really adds fuel to that ongoing debate about the best ways to handle those long, complex sequences of information. For a while, transformers were like the undisputed champs, but then SSMs came along, promising better efficiency and scalability.
But now that we're seeing these limitations with SSMs, does that mean transformers are, like, back on top? Or is it, more complicated than that?
Oh, it's definitely more nuanced than that. Remember, both architectures have their own pluses and minuses. Transformers might be better at those long-range dependencies, but they can be really computationally expensive. SSMs with things like polarization could be a more efficient way to go, but we've still got to address those robustness concerns.
So it's not a winner-takes-all situation. It sounds like the future of AI might be more about collaboration than competition, huh?
I think you're right. We might see those hybrid systems that use the best parts of both transformers and SSMs, or maybe we'll even come up with brand new architectures that we haven't even thought of yet.
It really does feel like the AI world is constantly changing, always full of surprises and possibilities. This research on SSMs, it's just one piece of the puzzle, but it shows how important it is to keep exploring and, like, critically evaluating these things. Got to keep pushing the boundaries of what's possible, but always with those ethical implications in mind.
Couldn't agree more. It's a journey of constant learning and discovery. Speaking of learning, if anyone's interested in, the nitty-gritty details of this research, I'd highly recommend checking out the paper itself. It's called Understanding and Mitigating Bottlenecks of State Space Models. It's really fascinating read, even if you're not, a computer science whiz.
Awesome. I'll definitely add that to my reading list. Well, this deep dive has been super insightful. Any final takeaways for our listeners today?
I think the biggest takeaway is that AI is a journey, not a destination. There will always be new challenges, new discoveries, new questions to ask. It's all about staying curious, staying engaged, and, staying informed.
Well said. And that's a wrap on our deep dive into the world of state space models. Until next time, keep exploring, keep learning, and keep questioning.